Hi, in this video we will learn about an important property of adjoint matrix, and we will see that a property provides us a method to compute inverse of matrix if the matrix is invertible. Okay, let us start with an example. Okay, we know that for 2 by 2 matrices, if I have a 2 by 2 matrix, 2, 3, 1, and say 5, then if we have a 2 by 2 matrix, the adjoint of 2 by 2 matrix is obtained by interchanging the entries on the main diagonal and multiplying off diagonal entries by negative sign. Let us just multiply the adjoint of A to matrix A. Both of them are 2 by 2 matrices, so we can multiply. And what we will, let me just write these entries and then go from there. 2, 3, 1, 5. Okay, here I can multiply this guy there. So 1 entry, this will be 10 minus 3, this will be 7. If we multiply, this will be 15 minus 15, this will be 0. That will be negative 2 times, negative 2 plus 2, this will be 0 again. Negative 3 plus 10, this will be 7. Let's do another one of these guys. In another video, we found the adjoint of this matrix 2, negative 1, 2, 2, negative 1, 1, 0, negative 1, 3. And we found the adjoint of that. So adjoint of A is was negative 2, 1, 1, and negative 6, 6, 2, negative 2, 2, 0. Okay. And what again, if we multiply adjoint of A to matrix A itself, so negative 2, 1, 1, negative 6, 6, 2, negative 2, 2, 0. 2, negative 1, 2, 2, negative 1, 1, 0, negative 1, 3. This is just matrix multiplication. An interesting thing is that, okay, so this multiplied there, we get negative 2 times 2 is negative 4, plus 2, this is negative 2. This guy multiply, first row multiplied to the second column, we get 2 minus 1 minus 1, 0. First row times third column, you get negative 4 plus 1 plus 3 is again 0. Second row, first column. Second row, second column, we get negative 2. Second row, third column, 0. You continue this thing. And as you can see in these two examples, if I multiply adjoint of A to A itself, we always get this multiple of identity. And there's this number here. This number is 7 times identity. Here what we have is negative 2 times identity. Well, this is the key property of the adjoint. So this is the theorem, which says that if you multiply any matrix, square matrix you find, you multiply adjoint of that matrix to the matrix itself, you're going to get always a matrix which is multiple of identity. So it means that only on the diagonal we will have non-zero entries, and all of them are equal. Yeah, even on the diagonal we can have all zero, but all of the entries on the diagonal will be same number, everything else zero. That number is exactly determinant of A. Well, you can compute determinant of this guy. You will see that that is -2, and determinant of this 2 by 2 matrix is 10 minus 3, 7. That's exactly what we have there, And that is the key point there. Why? Because you see, corollary of this thing will be, we already know that if A is invertible, if determinant of A is non-zero, then I can multiply the determinant to the other side and you get 1 over determinant of A, which is a scalar, multiplied to adjoint of A. This whole thing multiplied to A will give us identity. So we found a matrix. When we multiply to A, we get identity. That means that we found the inverse of that matrix, which is 1 over determinant of A times adjoint of A. So this is another way to compute inverse of an invertible matrix. You find the adjoint of A and multiply it by 1 over determinant of that matrix. Well, note that before we had a test determinant used to check if a matrix is invertible or not. Now, with this fact that you have here, you see that we can also use determinant to find the inverse, because you see the entries of adjoint are cofactors, which are basically determinants, yes, and 1 over determinant multiplied to that is the A inverse, and we computed using determinant. Then the second property, that is second corollary of this thing, is that, well, if this is true, which is true, so let me put this one so in the box. If that's true, you take determinant of both sides. So determinant of adjoint of A times A equals to determinant of, well, determinant of A is just a constant multiplied to identity. Here we have product of two matrices, so this will be determinant of adjoint of A times determinant of A. And on the other hand, here, this is a scalar. Scalar comes out of determinant but picks the power, the number of rows, and determinant of identity. Now you see that determinant of adjoint of A, if determinant is non-zero, you will see that I can multiply, divide this guy to the other side, and we get that determinant of A to the power n minus 1 is what we get. Determinant of identity is always 1. And also what it says is that what if determinant, if A is not invertible, the adjoint is, the determinant of adjoint is also 0. So let me just bring this to the middle, and that's the next corollary of this fact. So we have, if you multiply adjoint to A, you get multiple of identity, determinant multiple of identity. Then we can use that fact to find A inverse, and use that fact to find determinant of adjoint matrix. Okay, so having all these things said, now it's time to do some examples. Let us paste here what I have. Okay, so we are looking for the inverse of this matrix. So here I have to first find the determinant of this matrix. Let me call it A. The determinant of A is going to be 1 times 3 minus 2 times 5, which is negative 7. And adjoint of A, here for 2 by 2 adjoint, you know how to do. Interchange the entries on the main diagonal, multiply off diagonal entries by negative sign. And having those there, then we can find A inverse, which is 1 over determinant of A times adjoint of A. This is 1 over negative 7 times this matrix. Remember that before we had one way to do AI, row reduce it. If you get I to something, then that something is the inverse. So here, this is negative 3 over 7, 5 over 7, 2 over 7, negative 1 over 7. Well, this one B, let's first find the determinant of B. If we expand along the first column, what we will get is, well, negative 2 times 4 minus 2 minus 1 times negative 2 minus 0 plus 0. And then this is negative 2 times 2 is negative 4. And here we have a plus 2. This is negative 2. Well, here you have to find the adjoint. It will take a little bit time, but you can do this one now yourself. You can find the adjoint of, let me back to black, adjoint of B, and you'll see that the adjoint of B has these numbers. So 2, 2, 1, 2, 4, 2, 2, 4, 3. I'm just doing quickly these ones because, you know, there is 9 cofactor to compute it. You need to spend a little bit time. You can do it. Practice, please do it yourself on your paper. Pause the video and do it, and you will see that you get this number. So then, as a result, the matrix, the inverse matrix for this guy is 1 over negative 2 times 2, 2, 1, 2, 4, 2, 2, 4, 3. And this is negative 1, negative 1, negative 1 over 2, negative 1, negative 2, negative 1, negative 1, and negative 2, and negative 3 over 2. Well, knowing this fact would be nice when you're interested only on 1 or 2 entries of A inverse. For example, this is 4 by 4 matrix. It is invertible. Why is it invertible? Because the determinant of this matrix is upper triangular actually, and its determinant is product of the entries on the main diagonal. So oops, I need another negative 2, and it is non-zero, so A is invertible. Now the question doesn't ask for the whole A inverse. It says what is 1, 3 entry of the A inverse. So let me just put some space here. 1, 3 entry of A inverse is going to be, well, 1, 3 entry of 1 over determinant times adjoint. So it will be 1 over determinant of A times 1, 3 entry of adjoint of A. But we know that the determinant is negative 18, and 1, 3 entry of adjoint is nothing but 3, 1 cofactor of A. So means that we have to find 3, 1 cofactor of this matrix. Let me just clean a little bit this guy here. So 3, 1, 3, 1. So this is 3, this is 1. And this will give us negative 1 to the power 3 plus 1. Then determinant of 2, 1, 4, 1, negative 2, 1, 0, 0, negative 2. And well, this guy, this is negative 18. This guy here is negative 1 to the power 4, which will give us positive 1. And we have negative 18. How about this one here? Okay, I can expand along the third row. This will be plus, minus, plus, minus, plus. So it will be 0, minus 0, plus negative 2 times the determinant of this submatrix, which is, not that one, sorry, this one, which is determinant of 2 times negative 2 is negative 4 minus 1. And all together, this gives us negative 5, and then times negative 2, 10 over negative 18. As you see, it's just based on the fact that the inverse is multiple of adjoint matrix. We found that. Let us do one more of this. So we have we are looking for a 1,4 entry of A inverse. This is going to be basically, let me write it in a little bit different way. A inverse is 1 over determinant times adjoint of A. So we are looking for 1,4 entry of that, which is the same thing as 1 over determinant of A times 4, 1 cofactor of A. Very nice. And while here, this is 1 over negative 18 times 4, 1, negative 1 to the power 4 plus 1, determinant of 4, 1 submatrix. So 4, 1, the submatrix is 2, 1, 4, 1, negative 2, 1, and 0, 3, 4. Okay. Now that we have everything there, I can shift a little bit again lower, and we'll find negative here. This is negative 1 to the power 5, so we'll have another negative sign. This will cancel with that negative there. And then the determinant, I'm expanding along the first column, plus, minus, plus. So 2 times determinant of submatrix, which is negative 8 minus 3, minus 1 times 1 times 4 minus 3 times 4, plus 0 times something. This is 1 over 18. This is negative 11, negative 22 here. And here, this is negative 8 plus 8. That plus that is negative, 14. And, well, we have the entry negative 14 over 18, which is negative 7 over 9. And you saw this gives us a good option of doing the computations for entries of determinant, entries of A inverse. Okay, and last example, this is the property, the second property. We learned that determinant of A adjoint of A, you can compute, and it is just determinant of A to the power n one less. Yes, this is what we have here in this box. Yeah. And well, okay, now we have to compute this guy. Well, right away you go here. The second one is asking for determinant of adjoint. This is determinant of a to the power what? This is n is the number of rows. This matrix has 4 rows, so 4 minus 1. This is 2 to the power 3, which is 8. How about adjoint of a times a? You multiply adjoint of any matrix to that matrix, you will get an multiple of identity. So let me write this. Determinant of a times identity. So in other words, what we will get here is 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2. You don't need to do any computations here. Well, as you saw, everything started with one property of the adjoint matrix, that when you multiply adjoint matrix to the matrix itself, the result would be determinant of A times identity.